Okay, let's get started. So, in the previous class, so actually, we learned about the power consumption, of a computer system, and then we learned how to calculate the dynamic power. So so actually, the the power consumption is composed of the static and dynamic power, dynamic power and static power. So, uh, so it's related to the some it's a hardware design and then semiconductor technology. So actually the dynamic power is consumed when a computer is working. Okay, so it means that when the signal is changed, so we learned that digital system handles digital signals, right? And then a digital signal is composed of zeros and ones. So working means that the signal values are changed. So 1 to 0 or 0 to 1. And then in the electric circuit, when a signal is changed, and so actually this signal is represented as a voltage level, right? So which means that signal is changed. It means the voltage level is changed. Okay, so it's related to some, it's an electric circuit or hardware design. So it may be a little bit tricky, but so it's just a common sense, right? It's a common knowledge. Okay. So anyway, when a signal is changed, uh, electric power is consumed in a circuit. Okay, and then this consumption is called dynamic power. And but uh, in a real semiconductor circuit, the power is consumed even if the signal is not changed, right? So this is caused by uh, the non-ideal property of CMOS transistor. So actually, the CMOS transistor does not consume electric power if this transistor does not work. Okay, so it's an ideal property, ideal property of the CMOS transistor. But this is an ideal, okay? And then we live in a non-ideal world, right? So because of non-ideal characteristics of the CMOS transistors, a circuit consumes static power, even if this circuit does not work. Okay, so and then this power is called the static power. So actually, so in the previous class we learned about only dynamic power. Okay, so, it is because the actually in an old computer system, dynamic power was dominate. Okay, so the most power consumption was dynamic power, but it was changed. Okay, so actually, as the transistor size is reduced, then static power, the portion of static power has increased. Okay, so and then recently the static power also occupies the nearly half of the total power consumption of a computer system. Okay, so static power is also critical in in a modern computer system actually. But in this course, we will only learn about the dynamic power consumption. Okay, okay, so we learned about the end of the narrow scaling and then why the architecture is changed to the multi-core architecture. Okay, and then we learned about the benchmark. So benchmark is an application that is used for measuring the performance of a computer system. So we require the commonly used application to measure, to compare. I explained that in order to measure the performance of a computer system, we need to compare. We need to compare the performance with the reference machine, right? That's what we learned in the previous classes, right? So we just compare the performance. So which means the X is faster than Y. Right. So there. Okay. So blah blah times, right? That's how we measure the performance. Okay. And then the benchmarks, we use benchmark applications for measuring the performance. This is the standardized applications. Okay. So we learned about the spec benchmarks, right? So also the spec includes the different types of benchmarks. So we can use this benchmark for measuring power consumption of a computer system. So this benchmark is called spec power. Okay. So in order to measure, so actually we can measure the power consumption of our computer system by measuring the current level, to the power supply machine. Okay. So anyway, so we can run the spec benchmark application, spec power benchmarks, and then we can measure the power consumption of a computer system. And then, but our computer system exhibit some interesting, interesting uh, power consumption characteristics. So, so it means so actually the power consumption of a computer system is not proportional to the workload, the the load in the computer system. So it's a load. So in actually, I believe so. If you use the laptop, then you can measure the load, the CPU load in on your computer system, right? So if you use the Windows operating system, you can click the Control Alt Del, and then you can launch the task manager. Then you can monitor the CPU load. So if CPU load just exhibit the amount of workload compared to the maximum the the maximum workload that can be run by CPU. Okay, so and then we expect that the CPU consumes power proportional to the amount of workload. Right. So actually, we expect that we can uh, uh, we can get paid based on our amount of work. Okay. Uh, so and then we just expect that our pay is proportional to our amount of work, right? But so it's not true actually. So anyway, in a computer system, so actually we expect that the workload, the amount of work is proportional to, actually the power consumption is proportional to the amount of work done by a computer system, but it's not true. So this is the example. So this is the workload level, and then this is the power consumption. So if the workload level is 10%, the 10% of the maximum capability of a CPU, but this computer system consumed 15 watt. How about the 100% load? Then it's around the 350 watt. So if we just compare these values, then you can observe that actually the workload is just 1/10 of the full workload, but the power is consumed around the 1/3 of the full workload. Okay, it's not proportional. Okay, so then what do we do? So it means, so actually we want use a computer system efficiently, right? What does that mean? Efficient use. So you can think that this is cost. So it's money. Okay, you need to pay money for the electric power. Okay, but this is the amount of work. So which is better? So if we just consider the efficiency, then we can observe that this scenario is the best scenario, right? Because the efficiency is the highest. It shows the highest efficiency. So actually, in order to get the most efficient, in order to achieve the most the highest efficiency, then actually we need to keep the workload level as 100% of the full workload, the the capability of a computer system, right? So compared to this, then this efficiency is low, okay? Because the 1/10 of work is done with the 1/3 of electric power. And then this is called the power in proportionality of a computer system, okay? So actually, it's very critical. It's very critical for the data center design, okay? So as I mentioned, the big companies like Google or Microsoft or Amazon, so they run very large data center. Okay, so and then the data center consume electric power. So so, so hugely. Okay, so then what do we do? Actually, in order to get the highest efficiency, then we set the the load level of a computer system as 100%, right? In the data center. So which means that the data center has many computers, and then only the small number of computers, the load level is 100%, and then some computers are power off. Then we can get the highest efficiency, but it is not easy. Okay. If we just turn off this computer system, then the the problem is that so we cannot use our computer resources, right? And then sometimes if the many requests are given to this data center, then this data center cannot handle these requests in this case. So in the data center, we need to set some appropriate the workload level for the entire computer systems, right? So this is very interesting, right? But it's obvious, right? So it is because, so firstly, so the computer system is an electric device. So even though the CPU does not work, the other components such as the network adapter and then uh, the power supply, and then some some peripherals, so they consume power, right? Also, another reason is static power. So as I mentioned that the CPU also consumes static power. So which means that even though the CPU is not working, the CPU consumes power. Okay. So that's why. So even though the workload level is low, then a computer system consumes power. Okay. Okay. So power is also very critical. Okay. So if you are so if we are So if you are interested in working on computer architecture or computer hardware, then you need to focus on firstly performance, and then the second power, the cost. Okay. Okay. So now let's learn about the Moore's law. So actually the Moore's law. So I believe some of you have heard of the Moore's law. So it's very famous, and then it's very popular. So what is Moore's law? The performance or number of transistors, will double or triple, double every 2 years. So this is Moore's law. Okay. So actually the Moore's law is not theoretical law. Okay. So I also copied the definition of Moore's law from Wikipedia. Okay. So this is just observation. It's not theory. Okay. But it is called a law, right? Even though it's not a theory. So it's just observation. So, and then the Moore is also the person, right? So Intel, one of Intel founders, right? So the circuit, the dense. So number of transistors in a dense integrated circuit like a CPU doubles about every 2 years. Okay, so it just explains the trend of semiconductor technology. Then why is Moore's law so important in a computer industry or CPU industry or semiconductor industry? So it's a Gordon Moore. Actually, he died. So actually, where is it? So I showed this graph. So this chart shows the performance of the single core processor, and then I mentioned that for this period, we can we was able to increase the performance of a CPU dramatically and then exponentially. Why? It's because of the advances in semiconductor technology. And then Moore's law explains this trend, the advances in semiconductor technology. And then Moore's law explains how fast or how the trends, this technology uh, has changed. Okay. So based on the Moore's law, we can just estimate the trend of semiconductor technology. And then based on this trend, the CPU vendors such as Intel or AMD can develop their next version of CPU, next generation of CPU. Then the customers expect that, oh, the next generation CPUs will exhibit higher performance because the transistor has changed. So the CPUs use better transistors, right? Faster transistors, right? So they can expect that, oh, new CPUs will faster and better. Okay. So Moore's law just to explain that new CPUs or new semiconductor devices will exhibit the higher performance or the, the better characteristics because of the changes in the semiconductor technology. Okay, so that's why the Moore's law is so important. So this graph shows the number of transistors in on in a CPU. Okay. So you can find that this y-axis is also the log scale axis. So and then this is year. So linearly increased. So which means the number of transistors has increased exponentially. Actually, the Moore's law explains this trend. Okay, and then so this is 2016. So actually, someone expected the Moore's law will end soon, and then that's actually around the uh maybe around the 20 years ago, the Golden Moore. So actually, Golden Moore. Golden Moore is so Golden Moore. Actually, Golden Moore told the Moore's law, and then he estimated that Moore's law will and soon, around 20 years ago. So it is because it's very hard. It's very hard to make transistors smaller and smaller. So think about this number. It's a 2 nanometer or 5 nanometer. So you may think that it's just a number, but it's a 2 nano. It's it's comparable to the size of elements like 분자, right? So actually this number represents the width of the transistor channel, and then actually the electron pass through this channel. That's how the semiconductor works, right? Anyway, so this width is nearly very small. It's around the tens or hundreds of element size. It's very difficult. It's very difficult to make smaller transistors. So even Gordon Moore believed that the Moore's law would end soon. But fortunately, the companies such as TSMC or Samsung have developed the advanced transistor technology, transistor node. Okay, so Moore's law has continued, but it may end soon. It may. Okay, maybe the TSMC may develop the lower than 1 nanometer technology, maybe, but it's very hard. Okay, so this is the microprocessor trend. So Moore's law continues. So maybe fortunately, but because of power, so I explained that the frequency is saturated. So nearly the frequency of a CPU is the same. So even though we purchase the new generation of CPU, the clock frequency is nearly the same. Okay, and then single thread performance, it's a slightly increased, but it is being saturated. And then also TDP, the power is saturated, but is increasing recently. But so you can find that the number of cores increased. So actually, from this year, so we can continue Moore's law by increasing the number of cores in a chip. Okay, we do actually the CPU vendors do not make larger CPU, larger core, okay, larger single core. Instead, they have increased the number of cores in a chip. Okay, so because of power. So okay, so this is a trend of Moore's law. So you can find that. So it's Intel. So Intel is struggling recently because of they have difficulty in developing the advanced semiconductor technology compared to TSMC. But anyway, you can find that this is the ideal trend, ideal graph by Moore's law. But you can find that the trend, actually the Intel technology cannot follow the Moore's law. Okay. So okay, but the Moore's law is still important because actually the CPU vendors, the semiconductor companies try to follow the Moore's law. Okay, and then they have developed the semiconductor technology, so and based on the Moore's law. Okay, so these are 8 great ideas in computer architecture. So which means that so we can the computer architect or computer architecture researchers have developed the have developed the computer system based on these ideas. Okay, so the 8 ideas, the design for Moore's law. So Moore's law. So based on the Moore's law, they have developed the processor design, and then abstraction. We learned about the abstraction, right? So we, in order to simplify design. So this approach is important because based on some abstraction concept, we can understand the very complex system. Okay. Also, we can simplify design using the abstraction concept. And then, so these are important for processor design. Make the common case fast. So what does that mean? So think about this. So your work is composed of 90% of task A and then 10% of task B. Then you can work hard, then you can improve the performance for this task B by 99%, right? So it becomes the 1% of time. It is 99, no, 90%. Okay, 90%. Okay, it's a huge improvement. So we can reduce this 10% of task into the 1%, right? So 1%, it will consume 1% of total time. Then what is the improvement? Improvement is just around the 9%. Even though we improved this part 90% by 90%, but the total improvement is 9%, just because the portion is so small. So this is the large portion. So in order to improve the total the performance of this system, we need to focus on this large portion. Okay, this means to make the common case fast. Okay, and then performance via parallelism, pipelining, prediction. So we will learn about the pipelining in chapter 4, and then parallelism also in chapter 4. Okay, the prediction, this is the advanced uh, concept. And then hierarchy of memories. So we will learn about the memory hierarchy in chapter 5. Okay, and then dependability, yeah, redundancy. So it's a reliability issue. Okay, so these are some ideas for developing better CPUs, okay, or better computer system. Okay. Okay, so this is the end of chapter 1, and then we will jump to the, let's see. We'll jump to chapter 2. The chapter 2 will cover instructions. So actually in chapter 1, we also learned about the concept of instructions, right? So actually you can find the instruction count, right? And then CPU actually execute instructions, okay? So in chapter 2, we will learn about the instruction, the language of the computer. Okay. So actually in the not this. So that's the textbook of the advanced computer architecture. Then you can find that this figure. So you can find that. So it's a software and then hardware, and then hardware is under this large plate. And then what is this plate? This is the instruction set. And then, so you know, the software is a plane, okay? And then the hardware is supporting the this plate, right? And then using instruction set. So how do you guys work hard? And then software guys are just playing. So anyway, so this figure explains that instructions are interface between software and hardware. Okay, so in order to understand how a computer works, then we need to understand how instructions are processed by a CPU. Okay, because software, we just write the high level language code, okay, like using C or Java. Python is a high level language code, but it's an interpreter language, not the compiler based language. And then this high level language, actually the software engineers just focus on this high level language code. So we can understand easily. And then the high level language code just use the, the natural languages such as English, right? Okay. But the computers cannot understand these high level languages. So it needs to be translated to instructions, right? It needs to be translated to the instruction. And then this instruction is given to hardware. Then hardware execute instructions based on the instruction set architecture. This is kind of document that collects the how the instruction is executed in a CPU. So it means the instruction set architecture just defines about the instruction in like the, so this is the instruction at R1, R2, R3. And then if this instruction is given to CPU, then it performs the R1 equal R2 plus R3. So it is defined. It's like the promises, okay, like or protocols, okay. So instruction set architecture just define the behavior of instruction, and then the hardware is designed based on the instruction set architecture. So you can understand that the instruction is just the interface part between software and hardware. Okay, then how can we understand the processor? So you can understand a processor like this figure. So can you see? The instructions are given to processor, and the processor creates the result. And then I mentioned that the results are defined in instruction set architecture. So anyway, the processors create result. Then what are results? So we can say the result of instructions are changes of state. What does that mean? So actually, the computer includes the many memory components, right? Memory components, and then we store data in these memory components, right? So instructions actually change the data in these memory components, but instruction set architecture just define the memory components as the registers and main memory. So instruction set architecture just to focus on data in registers and main memory. Even though a CPU includes many different types of the memory components, but the instruction set architecture just define the result, the change of data in registers and main memory. Okay, so change of state means that the data in registers are changed, or data in main memory are changed. Okay, so you can understand like this. A computer execute instruction, and then a CPU execute instructions, and then CPU creates the change of state, like it's a result of instruction. And then these results are changes of data in registers and main memory. And that's it. The instruction set architecture just define this input, the instruction, and output. The result by a CPU. Okay, but there are many different types of instructions, right? So think about this, the high-level language code. So your high-level language code will require some many different kinds of operations, right? So also the instruction set architecture just define the different types of instructions, such as arithmetic or logic instructions. It performs the arithmetic operation or logic operations, and data transfer. Data transfer means so like the load and store instructions, and control or the branch instructions. So we will learn about these instructions. And as I mentioned, the instructions make change of states. So, and then it mentions the architectural states. So it includes as I mentioned, the register files and main memory. So you can understand, you can just understand that, oh, instruction is given. So your high-level language code generate many instructions, right? And then actually compiler generate the many instructions, and then these instructions are given to processors one by one. Okay, like so I will show the example of instruction later, one by one, and then CPU creates the result of instructions also one by one. Okay, so for example, so add x1, okay, because the RISC-V used the x1, x for the register, and then sub x3, x4, x5, and then multiply x4, x5, x6, x7, blah, blah, blah. So there are many instructions, and then these many instructions are given to a processor one by one. It means sequentially from top to bottom. Then a CPU generate the result of instructions also in the order of instructions, because so it's a first, it's a second, and it's a third instructions. So CPU generate the firstly the result of the first instruction, and then the result of the second instruction, and then the result of the third instruction. Okay, you can understand the behavior of CPU like this. Okay, and then that's how the software engineers understand the CPU. It means actually the real behavior may be different, but on the simplified view, we can understand a CPU behavior like this. Okay. Okay. So instruction set architecture, the ISA. So it's a ISA. So it can be called ISA or ISA. Okay. So sometimes I can use the word ISA. So because it's an ISA. So ISA defines a CPU or CPU family. So for example, there are two popular ISAs, the instruction set architectures such as x86 and ARM. What does that mean? Instructions of x86 are different from the instructions of ARM. So ARM is a company. So x86 was invented by Intel. Okay, so these companies just define the result of instructions based on the result of instructions defined. Okay. Also, ARM is another company. ARM defines the result of ARM instructions. So what does that mean? x86 CPU cannot execute ARM instructions because x86 just execute the defined x86 instructions. If x86 receives undefined instructions, then the CPU cannot execute these instructions. Do you understand? So the ARM processors cannot execute x86 instructions. Okay. So instruction is a collection of instructions. Also, it defines the output, the result of instructions. Also, the instruction set architecture includes the memory and registers. So obviously, because the instructions make the result is a change of states in register files and main memory. The ISA, the instruction set architecture, also define the memory structure and registers, such as the number of registers and then the size of registers. So we'll learn about registers later. Okay. So you can think that ISA is the contract between the software and hardware, right? It's a promise. Okay. Then sometimes you can, we need to distinguish the ISA, the instruction set architecture, and the microarchitecture of CPU. So it is because we frequently use the term architecture for mentioning the ISA, the instruction set architecture, or the microarchitecture of a CPU, but it's different actually. So for example, x86, Intel Xeon is a server CPU, and then Intel Celeron, it's the kind of a mobile, or actually the Celeron is dead maybe. Anyway, the Celeron is the another family of Intel CPU. It's for mobile devices. So Xeon and Celeron can execute x86 instructions, right? So which means, oh, Xeon is the family of, so it's a kind of x86 CPU. So it can execute x86 architecture, instruction set architecture. Celeron is the same. Celeron also is a Intel's CPU brand. Celeron can execute x86 instructions. So we can say that Celeron is the x86 family. So it's the instruction set architecture family. But the microarchitecture is different. Okay, so microarchitecture defines how the CPU is designed. So it just defines the core architecture, okay, core structure. So the architecture can be different, the microarchitecture, and then it means the microarchitecture. Okay. So instruction set is the repertoire. So it's the list of the instructions. Okay. So And actually, if you visit the resource tab of Piazza, then you can find some resources, right? So the materials. Then they in the table, the material, maybe I forgot the name, the material table, then you can find the RISC-V instruction set architecture manual. Okay, so it's just the manual. So this manual defines the RISC-V ISA, the instruction set architecture. It means it defines the instruction, RISC-V instructions, and the result of instructions. So you can read the manual. So if you are interested, okay. So instruction set or instruction set architecture is the repertoire of instructions, okay. And then it also defines the registers and the memory, okay. So in this course, so we will learn about the RISC-V ISA, the RISC-V instruction set architecture. So RISC-V is the RISC type ISA. What does it mean? What is the RISC? So R means the reduced, I is the instruction, S is the set, C means the computer. So RISC represents the reduced instruction set computer. And then the opposite concept is the CISC. It's the same. C means the complex. Okay. So we can say that ARM is the kinds of RISC type ISA, and then x86 is the CISC type ISA. Then what is different? Only one word is different. So reduced and complex. So what does it mean? The RISC type ISA is simpler. Okay, so it's a reduced instruction set. The CISC type ISA is handles the complex instructions like X. So if you read the, so you can also find the x86 ISA manual in the internet, right? Then you can read the x86 ISA manual. Then you can find, oh, it's so complex. Instructions are, there are so many instructions, and then instructions are so complex. But the RISC type ISA, so it's actually instructions are simple, and then so actually the number of instructions is also it's a smaller. Okay. So what is RISC-V? So in this course we will use RISC-V for explaining ISA and process design. And what is RISC-V? RISC-V is the open source ISA developed by David Patterson and John Hennessy. So it's developed at UC Berkeley. Okay. So what is open source ISA? It means the x86 and ARM is not open sourced. So which means in order to use x86 ISA or ARM ISA, then companies need to pay royalty, pay money for using these ISA, because this is not, these ISAs such as x86 and ARM are not open sourced, but RISC-V is free. So we do not pay royalty to this RISC-V. Okay. And then RISC-V is developed actually 10 years ago, maybe. So it's a very new ISA. Okay. So it's organized, organized, and then it's simple. Okay. Okay, you can, if you are interested, you can click the slides or a video link. Then you can also get information for RISC-V ISA. Okay. Oh, where is okay. So this table just compares the ARM and RISC-V. So ARM is also RISC type ISA, but so it's announced not 2011. It's an ARM V8, okay, and then RISC-V. So then you can find the ISA manual size. Okay, even though ARM is the RISC type ISA, the ARM has longer history. So as the if ISA has longer history, so it means that the ISA includes many new instructions. So for example, x86. x86 has very long history. Okay, it was developed around the 1970. So it has 1,300 instructions. So it means very complex. And then there are many instructions. Why? It is because Intel need to add new instructions to make more efficient CPU, right? New instructions were required. So that's why Intel added the new instructions in the x86 ISA. So actually the number was very small, but it has been increased. Okay. Then RISC-V is designed for research, education, and commercial. And then there are smaller number of instructions. Also, it's well organized. It is because it has a short history. It's because it was developed recently. Okay, so it's some design policy of RISC-V ISA. It's a simple and clean state design because it's new, and then it's a modular ISA. So modular means that actually the baseline ISA is the integer ISA. So integer ISA represent that instructions handle integer data. Okay, so integer ISA just define instructions that handle integer data, right? It's very simple. It's a baseline ISA of RISC-V. Okay, and then if we need, then we can add some extensions, extended ISA. Like if we require integer multiply or divide instruction, then we can add the M option, M extensions. Okay, so it means multiply, and then if we require atomic memory operation, then we can add A, and then floating point, we can add F extensions, and then D, the double precision, then we can add the D extensions. So if we need, we can add extensions to the baseline ISA. So actually, we will practice the RISC-V compiler, right, in the lab. Then you can find some options. And so compile, you can compile. So you can build a RISC-V compiler using these options, okay? So you need to build. It is because, actually we do not use RISC-V processors for our laptop and smartphones. Usually our laptop includes x86 CPU. So if you purchase the Intel or AMD CPUs, which means our laptop can only run x86 instructions, not RISC-V, right? Do you understand? So ISA is totally different. But we need to practice. So we need to run RISC-V instructions using our laptops. How? we can use the simulator as a software, and then we need to build compiler, the RISC-V compiler. So then you can find some options like M, A, F, D, like here. So it's because the RISC-V is the modular ISA. Okay, we can add some functions or instructions if required. Okay, it's a simple, and then this is the some examples of the RISC-V instructions. Like you can find the shift, arithmetic, and logical branches, blah blah blah. And then these are instructions. Okay, we'll learn about the instructions later. Okay. So this was the brief introduction to the RISC-V ISA. Then let's learn how a program is executed in a CPU. Okay, so as I mentioned, the CPUs cannot understand high-level language code. So the high-level language code need to be translated. So actually the CPUs can only understand the digital signals, 0 and 1. So the compiler create the assembly instructions, the assembly code from the high-level language code, and then assembler translate these assembly instructions into the machine instructions. But you can find, so actually the 1-9, so in the assembly code, this is the 1-9. This 1 line of instruction is mapped to the 1 line of machine instruction. It's nearly the one-to-one mapping. So from assembly instruction to the machine instructions. Okay. But this is not one-to-one. So actually the compiler generates the assembly instructions from the high-level language code. That's how the high-level language codes are compiled and the machine instructions are generated. So it means actually the CPU receives these instructions, this type of instructions. So if you just see this one, then can you understand? It's just 1 and 0, and then it means these instructions are digital data. So what does that mean? Actually, you know, so if you took the digital logic design course, then it's a digital data. The digital systems handle digital data, and then it's like a 0, 1, 0, 1, 1, 1, 1, 0, 0, 0. So this is the data, and then another data is the something like this, 1, 1, 1, 1, 1, 1, 1. Okay. So these are data. And then if you see the instruction, this is a machine instruction, actually we cannot distinguish. So it's just a digital data, right? So you need to understand this. So instructions are also kind of digital data. Then where is the instructions in a computer? Where is the instructions in the computer, in a computer? I mentioned instructions are also kind of digital data. And where is the data? Memory, right? Data exists in memory. So what does that mean? Why did I explain this? So instructions are also in memory because instructions are also digital data. So this concept is called stored program computers. So you may think, oh, so because as I explained that the instructions are also digital data, and then all data exists in memory. So we can find the instructions in the memory. Then you can think that it's obvious. But actually, in the early computer system, instructions are separated from the data part. Okay. But the genius in the computer architecture is von Neumann, actually, uh, developed this stored program computer concept. Okay, so it means all data, including instructions, are in memory. Then how a processor can execute instructions. So I explained that the instruction is given to a processor and then processor generate result. Then how instruction is given. So this is the memory. So processor needs to read data, read instructions from memory. Do you understand? So instruction is given to a processor, so which means a processor reads instructions in memory. So this concept is called the stored program computers. Okay. Then how can you read? What is required? What is required for reading data in memory? Address, right? So address, so the memory is the 2D array that stores data, right? So you can just understand the memory is the very large array, like the M0, M1, M2, blah, blah. And then these indexes are address, right? So we can define arrays in our program, right? So arrays can store the multiple elements. The memory is the same. The memory is composed of many arrays with the same size. And then we can store data in the memory using in a certain array, in a certain element of this memory array. So which means in order to read data from arrays, what is required? We need to use the index of the array. And then this index is called the address. Okay. So which means in a stored program computer, the instructions are also in memory. So processor reads instructions from memory by using addresses. Okay. So you can understand this. Okay. You need to understand this. So this address is called the program counter. Okay. So you need to understand this concept. And then program counter is also called PC. It's an abbreviated form. So you can find the PC here. So this is the example of a compiled compiled code. Okay. And then it is okay. It's a compiled code. And then so in this example, you can find some numbers, the hexadecimal numbers, also another hexadecimal numbers, and then some letters. So this column shows the RISC-V assembly instructions. Okay. And then this column shows the RISC-V machine instructions. So this instruction, assembly instruction, is generated by compiler, and then assembler just generate the machine instructions. Oh, you may think, oh, this is the letters, but it's a hexadecimal number. So it is because, so if we just use the binary number, then length is so long. So that's why we use hexadecimal numbers, right? So this is the machine instructions. So it's, as I mentioned, assembly instructions are mapped to the machine instructions one-to-one. Okay? So it's encoded like this. Then what is this? You can find another hexadecimal numbers, and then these numbers represent program counter. It means address of instructions. So which means this data is in the memory with the address of 10074. Okay, so this is also hexadecimal number because the binary is so long. Okay, so you can understand the instructions, the instructions in the memory like this. Okay, so then in order to read the instruction, so actually this is the first line of the main function. So in order to execute the main function of this code, then processor needs to execute the first line of this code. How? Processor reads this instruction using this address from memory. Do you understand? So it means processor just change the program counter, this address, then using this program counter reads the instruction from memory, and then this instruction is executed. Okay, so like this. So you can understand like so like this. So this is the memory map. Okay, and then so this number represents the address, and then these are data in the memory, but actually it just shows the instruction part, instruction data. So using this PC then access this instruction, and then the processor can execute this instruction. Then in order to execute another instruction, the next instruction, then the processor just change the PC value like as the next line. So this is the next line. So PC is increased, and then it accesses the next memory, the next memory space. Then it just read the instruction from memory, and then this instruction is executed. That's how instructions are executed in a computer or CPU. So why is this is so important? So you need to understand. So actually this part, so from this part, actually we are going to the hardware area. And then I explain how hardware execute instructions. Okay, like so you actually so I believe you are familiar with the programming. So actually the programming is easy. So you can write code, and then the code is executed one by one. Actually the instructions are the same. If you just see the assembly code, then assembly instructions are executed one by one from top to bottom, like the C code. But actually, in a hardware, the instructions are like executed like this. A processor reads instructions using PC, and then the processor reads instructions from memory, and then this instruction is executed. And then the PC is changed to the next line, the 10078. Then the next instruction is executed, and then next line 1007C. Then the next instruction is executed. Okay. So what is stored in the memory? Instructions. Okay. So it's also, and then if we are actually we will have labs, but so if you so actually compiler can generate the assembly code, and then if you open this assembly code, you can just find this is the text, this is the data, like blah blah like this. So actually the code, the assembly code or the binary code includes this instruction and data used by our program. So instructions is also called the text. Okay. So what is stored in the memory? Instructions and data. And then actually our binary data also includes the global and static data. Okay. So if you learn the C language, then so you can just define as a global variable and static variable, right? So which means this data is also stored in the binary file. Okay. Also, we can dynamically allocate data using some commands such as the malloc, okay, memory allocation. So dynamic data is assigned to memory dynamically during runtime. So it is different. So actually does C is different from the Python, and then you can think that C is more difficult. It is because the C is kind of some low-level language, and then which means that the C is closer to hardware. Okay, so that's why C defines the global variable, static variable, and then we can also allocate the data dynamically. Okay, so okay, and then this is last topic. Okay, so how can you calculate the memory size? So how big is the memory of a 32-bit computer? So we learned that we can access data in memory using address. Then address is mapped to the memory space, right? Then what is the address 1? What is the size of address 1? It's 1 byte. It is equivalent to 8-bit. So it is called a byte address, which means address 1 represents the 1 byte of space. It's also important. Most computers use byte address, and RISC-V is the same. You can just understand that address 1 just maps to the 1 byte space. Okay. Then how big is the memory of a 32-bit computer? It means 32-bit computer uses 32-bit address field. So what is the maximum number? So it's 32-bit. So using the 32-bit, then we can represent until 4 giga. Okay. So giga is the 2 to the power of 3, and then also we have 2-bit here. So it's a 4 giga. And then address 1 represents the 1 byte. So we can support the 4 gigabyte of memory. And then this is the address range. Okay, so you can understand, it's also important because the hardware access the memory using the address, and then the CPU or the most computer use byte address. So 1 byte is mapped to the memory address 1 is mapped to the 1 byte of memory space. Okay, so I'll stop here and then thank you for your attention. See you in the next class. 감사합니다.